it's noon on the East Coast, so probably morning if you're not on the East Coast. And we've got 3 great panelists lined up today for Innovation Insights. So welcome to that. Just a couple points before we get started. Just remind folks of the IACMI vision and mission statement. Our vision is improving everyday lives through the power of composites. The mission is to convene, connect, and catalyze the composites community to accelerate advanced composites design, manufacturing, technical and workforce solutions to enable a cleaner and more sustainable, more secure and more competitive U.S. economy. And we organize ourselves around this tagline of convene, connect, catalyze. So what does that mean? It means I have this broad value offering to members in terms of networking, projects, co-funded opportunities, training, interns, facilities, expertise, influence on decision makers at various levels in the government and elsewhere, consulting and education. Just a slight reminder of that we did have our summer members meeting in Salt Lake. It was very well attended and quite the event. With social activities and the networking and those opportunities to gain value from your IACMI membership. So if you're not an IACMI member, this is just some of the things you get to experience. I want to point out that while the last few weeks we have been at the SPE Automotive Composites Conference in Detroit and IMTS in Chicago, we still have a couple of big events coming up. 2 of them very important is the CAMX. We'll see you all at CAMX in October. And then also at Composites World Carbon Fiber Conference in November in Greenville, South Carolina. So look forward to that. A little bit about Innovation Insights. 3 more scheduled for this year. The one in October will be the Monday after CAMX. The one in November will be the Monday after the Carbon Fiber Conference. And then in December, we'll make sure we get that in early enough so that for folks that will be out for the last couple of weeks of the year on vacation. So they're all the same time at noon to 1 p.m. And if you've missed any in the past, and we have them all archived on the IACMI website. So if you go to iacmi.org, you go to events, there's a tab, there's a drop down for Innovation Insights, and you can go catch the recordings for each and every one of these webinars going back to May of 2021. So today we've got a great lineup. Scott Blake, President of Aligned Vision, Eric Paul, President of Orenco Composites, both members of IACMI, and then Dr. Uday Vaidya, who is the UT ORNL Governor's Chair in Advanced Composites Manufacturing and the Chief Technology Officer for IACMI. So without further ado, I will stop sharing and we will turn it over to Scott. In the slideshow first and then do that.
I'm still seeing your screen. Okay, here we go. Let's see. Let me.
And I will say that if you've got questions, there is a Q&A and a chat box, so you can put them in either in the chat or the Q&A, and we will get to those questions as we go along.
Okay, thank you, Dale, and thank you everyone who's attending. I'm going to be talking about maximizing inspection accuracy and throughput with our large field, high resolution, AI enabled system with laser feedback.
So, Scott, you're not sharing yet, so we need to share.
Okay, hold on. I'm not. Okay, hold on.
The little square box with the up arrow in it that says share screen, that should help get you started.
I'm not. It says stop video, hide video.
You want me to run them for you, Scott? I have them right here.
Yeah, go ahead. Although
Yeah.
I'm not sure I can see you. I'm looking at my slide, but how do I get back over there? Geez, this worked perfectly before.
It did. We just tested it. Sorry about this, everybody. This happened.
Wait a minute. Here we go.
You got it?
This might work. Stand by. One more. It says I'm sharing now. Can anybody?
Yes, you are.
You are. Thank you, Scott.
Okay, let's see if it can move. Okay, good.
Yep.
Okay, I'm going to talk about quality monitoring and how much cycle time is involved with quality monitoring. A little bit about automatic inspection technologies in composites. And then I'll talk about what we're doing with a very large field of view and high resolution system that includes a laser projector to guide corrective actions. And the big news, especially from IMTS, is just how rapidly the ability of AI and deep learning are evolving to support these kinds of activities. Electro Impact did a study a few years ago with Boeing, and it turned out that only about a quarter of the cycle time in production was adding value. And a large portion of the non-value adding cycle time was in inspection and repair. And our goal is to bring this down as close to zero as possible. The challenges are we need really high quality inspection images in large, complex structures. We want to not disrupt inspection, and we want to enable rapid resolution of problems that are detected with automatic inspection. Right now, in addition to our machines, the principal method of inspecting automated composites uses a profilometer, which is mounted on the deposition head. And it's measuring distance to the surface by parallax and creating a surface profile. And it's not doing an absolute inspection. It's looking at things relative to each other or where the deposition head is. And when a problem is found, it's often difficult to know where to go physically on the part to fix it. On our largest parts, the envelope's almost 100 feet long, and you're looking for laps or gaps or twists or missing material or incorrectly located material that can be less than 0.5 millimeter. What we have is this machine called laser vision for large field automatic inspection. It's machine vision, not metrology. We are not creating point clouds. We're not using the laser for the actual analysis. We're aiming a camera with mirrors, a very high resolution camera that we aim with mirrors, and that allows us to multiplex a very large field. The data that we collect comes with a photogrammetric transform, which allows us to relate each pixel in our captured image to a region on the model surface. And then after we've analyzed the images, we can project guidance with the laser projector to show where additional inspection or remediation might occur. By doing machine vision rather than point cloud metrology, we're much, much faster than metrology. A long inspection cycle for us is about a second. And as I said before, each pixel on the 2D image is dimensioned and related to a region on the 3D model surface. We're essentially doing a gauging function. In the image on the right here, we've dropped digital calipers onto the ends of these toes, and we can tell where they are relative to each other, how wide the gaps are, all kinds of other attributes. And that image you're looking at is an example of highly magnified, high resolution image that was taken from 10 feet away, and those toes are 1/2 inch wide. On the Boeing 777X, this is an example of how our machine's used on the production of very large structures. In this case, this was a tryout wing spar. And you can see one of the laser vision machines mounted at the apex of that gantry. And the pyramid shows the field of view. And so we have a long standoff distance. We don't conflict with the deposition head. We can very rapidly aim the camera's field And we have a giant lens, much bigger than you would have on a smart camera, that collects lots of light, which results in very sharp, clear, high-resolution images. And in the bottom right in this image is, once again, toes taken from 10 feet away. And the photogrammetric transform allows us to plot tolerance bands from the nominal into the as-built image to see if the starts of the course are where they're supposed to be. And when we analyze the image, if we don't find what we're looking for, we point it out, as in the third toe in from the left, and we can use the laser projector to say, hey, this toe is not right. So we're effectively providing gigapixel resolution over large fields, 2, 3, 4, 5 meters on a side. And on the right, you can see a ghosted view of our system. The bottom half, the green cylinder, is a laser for a traditional laser projector, and it's aimed with very precise galvanometers, moving mirrors. Most of you are familiar with laser projection. And then that same data is aiming much larger mirrors for that giant blue lens. And we use the transform to focus the camera. We know precisely how far away we are because the transform brings the camera into the coordinate system of the part, and the precision of the optical aiming system effectively gives you a pan tilt system accurate to a fraction of a millimeter to capture the images. Here are some examples of attributes that we're working with. Just last week at IMTS, someone walked up and said, hey, I need to inspect honeycomb for various flaws. And he dropped a piece of honeycomb in front of us, and this is part of the imaging that we did for him at the show. And this could be a 10-foot square piece of honeycomb with complex shapes, and we can capture images of the fidelity and resolution that you're seeing there on the left. The top right picture shows us measuring critical fiber orientations on large, complex 3D surfaces. We're certified to an accuracy of plus and minus 1 degree. The purple band plotted on there is the angular tolerance for that material. The green line is the found fiber orientation. And as I say, we can capture and analyze images like this in around a second. We can actually create point clouds of orientations if you really wanted to look at how your material is behaving through an entire surface. The bottom picture on the right shows some FOD that we've detected in an image, and we're drawing boxes around it with our laser projector. And one of the great quotes about doing imaging, especially in large fields, is if you don't have enough pixels, AI can't learn. And we can provide images with tremendous resolution, lots of pixels in any area in a very large field. We also provide immediate feedback. We use the laser projector to say, there's a problem here. And this is a case of a discontinuity in an additive process where we're pointing with an arrow, or in an automotive assembly process where we're pointing with an arrow. This allows operators to quickly correct any problems that you have, and it minimizes production stoppage. It also provides data on how and when different flaws come into existence. As I said, each show I go to, I'm impressed at how rapidly the applicability of artificial intelligence is accelerating. We are reaching a point where analysis algorithms for any attribute can be developed very, very quickly, much faster than the old rule-based MATLAB kinds of machine vision algorithms. You capture images of good and bad things, you tag them, you treat them with a tool that develops classifiers, and you can build essentially intelligence for analysis, for automatic inspection for any kind of application. And our system supports running these models. We develop them. We have partners who develop them. We have customers who develop them. A lot of manufacturing research facilities are associated with universities, and universities are very big on AI and deep learning. And these algorithms get put on a special kind of processor. We use an NVIDIA Jetson. It makes the analysis models agnostic, and it also avoids all the kinds of problems you have with variations in the Windows operating system. Again, here's the Boeing 777X wing skin and spar cells. And we can look at anything unless we're being shadowed by the deposition head. And we can point back out anywhere in this 100-foot envelope, any place something is suspect in the images. And in this case, this is a fully integrated system. Our software development kit has enabled electroimpact to make our system a subcomponent of theirs. Everything runs seamlessly, the capturing of the imaging, the laser projection, the archiving of all the as-built data. We're also fully qualified on Sikorsky Blackhawk main rotor spars. These are, well, the Blackhawks are about 25 feet long, the 53Ks are in the 30s. And our qualification treats our system as an acceptable replacement for a trained inspector using calibrated instruments in where things are required for flight critical characteristics. Again, these are older models of our projectors mounted above an automated material handling system. Doing a lot of work in automotive, same kind of thing. We can fit most of a chassis into the field of the system. And we can even read stamped numbers on axles and things like that. We're doing a lot of work with electric vehicles and the battery trays. In additive manufacturing, we can see a lot of things that you don't see easily with metrologies, different kinds of discontinuities, droop and drool. We can sense cracks very well. Cracks are much easier to sense in images than they are in point clouds. We can look at porosity and FOD. That's the material I've prepared for today. I'd be happy to answer any questions. Thank you.
Thanks, Scott. I don't see any questions right yet in the chat, but let me just ask you, would it be possible to actually store and catalog the entire build history of a part, such that if something were to have an in-service question later and in the part's lifetime, say on an aircraft or on an automobile, you'd be able to come back and query that?
That's exactly what we do. We've been working with vision systems with Sikorsky for almost 20 years, and any Blackhawk main rotor spar, we can provide physical evidence that the critical characteristics were created properly through serial number and work order number and ply number. And we automatically archive not only the raw and analyzed images, we keep track of the certification of the device that's doing the automatic inspection, as well as all of the parameters that went into the inspection. For example, on the fiber orientation inspections, quality really only cares whether it's in or it's out, and they don't want anything to come out of production that doesn't have everything in. But we can also report how far off nominal it was, and we can look at trends or how much manufacturing variation there is. And this kind of knowledge or information is useful for reducing uncertainty, because there's a big gap between the nominal and the analyzed nominal and what goes on out on the shop floor. And we would like to be able to feed back quantitative data from the shop floor to adjust allowables and processes and modeling. And that's one of our goals, working with you and some of the other research organizations that we work with.
And let me ask you, the examples you show are, say, AFP with carbon fiber, for example. But I mean, what about, and some textile stuff? What's your experience looking at glass structures, fiberglass structures?
The only glass we can't really do well on is that's really transparent. It has to have a real surface. We don't want to be looking at what's underneath it. But most fiberglass we can do fine on. We can capture and analyze for any visible attribute. And fiber orientation is clear on dry glass, or most dry glass, and or pre-preg. And in order to be qualified on these various programs, we've had to demonstrate that we can truly see things, in a true positive sense, true negative sense, and avoid, the most critical thing to avoid is false positives. That is saying something's good when it's not. A false negative is acceptable, but they're very rare.
Okay. Question from our attendees, what is the resolution of the system? And does the quality of defect detection vary with image contrast?
The resolution is a function of how far away the imager is from the surface. We typically run in the 2 to 4 thousandths of an inch per pixel in about a 10-foot field. So it's very high res. And the angular resolution, as I said, we're fully qualified and certified for 1 degree. And what we do is, when we capture the image, we capture it with a transform. We understand the angle that of the facing of the surface toward the camera, and we can correct for keystoning and things like that. And 1 degree is actually tighter than a human can do with their eyes. I hope that answers the question.
Sure. Okay. I think we need to move on to our next speaker. And so thank you, Scott. If you stop sharing, and we'll move on to Eric. But I think you already have stopped sharing. I don't need to worry about that. So
thank you.
So yeah. So all right. Thanks, Scott. And again, if you have any more questions for Scott, just put them in the chat, and Scott will monitor that and answer them live. All right, Eric. We have Eric Ball, president of Orenco Composites. So Eric, stage is yours.
Thanks, Dale. Everybody, you can hear me okay?
Yes, and can see your slides.
Very good. So Scott, that was a very interesting talk. I'd have to say that's a long ways in the future from our iPhone photographs that we use to figure out, to see that we have plies in the right orientation, that they're actually there. I wish we could do something like that in our technology. Not sure it's practical at this point, but we're certainly not doing aerospace quality structures. But anyway, so the title of my presentation is Vacuum Infused FRP Tanks that enhance Orenco's innovative wastewater treatment technology. I'm a president of Orenco Composites, which is actually a division of Orenco Systems. And we're an engineering and manufacturing company based in Oregon. We have 3 divisions, as I said, Orenco Water, Orenco Controls, and Orenco Composites. We were born we were formed actually to develop wastewater treatment and collection systems for single family homes and on up to small communities of perhaps a few thousand people. We have worldwide distribution. We currently employ 475 people, and we have about 500,000 square feet in 3 facilities, all within a few miles here in Southern Oregon, about an hour south of Eugene. So like I said, we were formed to develop treatment and collection systems for single family homes and small communities, because what is available for conventional wastewater treatment is an activated sludge process. This is a picture of an activated sludge tank where you're basically blowing air into water to grow bugs that are going to treat the water, wastewater. And this is typical of I mean, that's a really, that's not a very technical description, but this is a typical process that's used for large systems all over the United States and all over the world. However, it doesn't scale down well for small systems, especially single-family homes or very small commercial systems. It requires highly skilled operators, lots of energy to operate, and it's just not a robust technology for low flows and intermittent flows. So in the 1980s, Orenco pioneered the development of packed bed sand filters for small scale wastewater. And while sand filters do provide the reliable, low cost, low energy, and low maintenance solutions that are inherent to packed bed filters, they do require significant on-site construction and land space, and repairs can be expensive, particularly if a system is abused or overloaded. So in the 1990s, Orenco developed a newer packed bed treatment technology called Adventex that utilizes a textile media housed in a factory-built fiberglass vessel. So in addition to the inherent benefits of a packed bed filter, Adventex allowed for a fully assembled factory-built unit that could be dropped in the ground, that minimized on-site construction and land space and simplified both design and system operation and maintenance. So here on the left is a single family home treatment unit. There's a textile media that hangs in there, and which actually is, so it's a fixed film packed bed filter. Bacteria grow on that textile, which treats the wastewater as water is pumped through that media. On the right is a what we call an AX100. It's a small commercial size unit. It's 8 feet by 16 feet, and it can essentially the system on the right can handle practically flows up to 20 to 30,000 gallons per day with multiple units. So here's what a single family home treatment system might look like. You can see just the lid, the rest of the treatment unit's buried. Had this been a sand filter, based on our earlier packed bed technology, it would have been perhaps 10 times that size, and you would have had a big media bed in your yard. Here's the larger AX100 commercial unit. This is a small subdivision, 25 homes, and it's got 2 of these 8 by 16 foot treatment units there. So this RTM'd AX100 unit really limited the practical size to, like I said, around 30,000 gallons per day. So it became readily apparent to us that in order to make Adventex practical for much larger systems, we needed to develop much larger vessels. Fortunately, during the early 2000s, we had been developing in-house vacuum infusion capabilities. And specifically, our interest was in developing foam core web stiffened structures. And we started by developing flat panels. This is one of our early panels we had built. It's about 8 feet by 40 feet, about 4 inches thick. We were using at the time Ti-Core reinforced foam core, which I'm sure a lot of you know is not commercially available anymore. We have early on, we actually developed what we felt was a stronger, better wrapped foam core rather than the Ti-Core. So our first large vessels were built with infused panels. This is a 2-story structure. It was on the bottom left, you can see some panels that are being seamed together. It's actually inside of an open top sea container. At the time, we don't use sea containers anymore, but you can see the top half has an operating room, because this is in Alaska. It's it's 3 hours north of Fairbanks. Excuse me, can get to be minus 60 degrees. So the operator needed a warm room to operate this system. So while these panel built tanks were lightweight and strong, they were really labor intensive, as you can see, involving multiple infusions and significant labor to bond these panels together. So our goal then was to vacuum infuse these large rectangular tanks in a single piece with, excuse me, with no seams and no joints. It was a pretty big leap for us going from simple flat panels molded on a flat table to a full rectangular 5-sided tank. So we spent some time figuring out how to infuse up a 10-foot vertical wall. Surprisingly, at least to ourselves, we found ways to do this just in a few weeks of testing. You can see here on the left, we've got a panel ready to be infused with multiple injection points. We actually learned that we could infuse up to 12 feet in height with just a single injection point near the bottom. So just in a matter of months, we were able to go from infusing flat panels to these large single piece rectangular tanks. These large tanks enabled prefabricated turnkey Advantex treatment systems on a scale not previously attainable. These large vessels called IACM treatment units provide the quality of a factory assembled product and fast deployment for municipal scale systems. So communities up to a few thousand people. They also allow for system scalability, an important feature for deferring system costs as a community grows. With activated sludge, it's oftentimes they need to build out the system for 20 years of potential growth, whereas our Advantex systems can be scaled and built basically by adding treatment units. So here's a treatment unit on the left. It's in the factory, just going through final assembly. It's got pumps and hanging textile media and nozzles and a bunch of other features in there. On the right, you can see a picture of a unit that's actually installed at a site. Here's a bunch of these IACM treatment units staged for shipping. They are sized so they just barely fit in a sea container. We ship these things all over the world. In fact, we have systems on every continent except for Antarctica. A few examples here. This is a treatment system on a hospital in Angola, Africa. These things can be sit on top of the ground or be buried right to the top of the lid. Here's a 300 home community treatment system in Ohio. It's got about 10 of these treatment units. Here's a resort in New Zealand, again, buried at grade. Here's some units that are sitting on top of the ground. In fact, this is a mobile unit. This is in Iraq, and they do exploration, oil exploration, and they move this from site to site every 6 to 12 months. Here's a mining camp in northern BC, actually on a glacier. You can see on the right there, they use helicopters to drop these things in place. So with our success in vacuum infusing these large rectangular vessels, it was clear to us that there are significant opportunities and value for the use of these structures for many other applications and industries. So we now build tanks and buildings for a lot of other industries. Our largest mold right now, we can produce a tank or a building that's 12 feet wide, 50 feet long, and 12 feet tall. Some of these things weigh over 30,000 pounds. This picture here on the right, that has 8-inch thick walls. It's a tank that's going to be completely buried underground. So a few examples of other tanks and buildings. This is a combination tank and building. So we infuse the rectangular structure in one piece, and then there's a couple baffles inside there, and so that we have tankage separated from actually a control room. That bottom left there, you can see it's a membrane bioreactor, and that's a skid with controls and pumps for a membrane treatment, which is a different technology than our Advantex. Here's another kind of combination building and tankage. Again, the main structure is infused in one piece. And of course, it's got control rooms and tankage and windows. And this happens to be for a selenium treatment at a power plant. Here's a much larger version of a selenium removal treatment. You can see those gray and yellow colored tanks. Those are all vacuum infused structures. And these happen to be filled with an activated carbon that's used in the selenium treatment system process. Here's an RV park. This has a whole bunch of our rectangular tanks. The tanks that you can see on the right are buried just at grade. Then there's in between those two tanks is a building, and then on the left there are two more combination tank buildings here. This is for a very large RV park in Maryland. Another example. This is in our factory, but it went to a manufacturer in San Diego for some sort of test tank. They take equipment and they drop it down through some openings down into a tank of some sort of liquid. We also produce buildings the same way. So instead of if you take one of our tanks and you turn it upside down, you kind of have a building. Although we do the bottom of the molds for buildings have a slope, a minor slope. So this is a 2-room 10 by 30 controls building. This actually went to a Frito-Lay plant. This is another common application for our buildings, a water booster station. Again, these buildings have no seams, no joints other than the openings for the door. Some other things that we've leveraged with our web stiffened structures. This is a 105-foot diameter concrete tank we designed. It has a bunch of 10-foot wide, some of them up to 55 feet long, and they're suspended by these steel trusses. This was a chicken processing wastewater tank, and this community kind of grew up around the outside of it. And just you can see on the upper beyond this tank, there's a elementary playground, and this is full of chicken wastewater, and it really stunk. Some of the other things that we do, just of note, we build web stiffened infused floating docks. This is an example of an 8 by 16 floating dock. Just this past winter, we were given an innovation award for this dock at the Miami Boat Show. We've started building vacuum infused bridges based on Infracore technology. We have a North American license to produce bridges, lock gates, and other structures based on Infracore technology, which there are now over 1,100 of these bridges, primarily in Europe. Here's an example of actually a traffic bridge built on Infracore. And here's a pedestrian bridge here on the right. Just a really brief rundown on Infracore. So it's kind of based on an I-beam concept. If you have a steel I-beam, it's a optimized strength, obviously. So with the Infracore technology, basically we're taking glass fiber and putting it in the shape of a beam, but it's put together in this fashion, like this, much different than kind of conventional wrapped foam web stiffened technology like we use for making our tanks. And the reason this is so important is that it really gives a robust sandwich structure that's damage tolerant and prevents crack propagation. The last couple of things, we've actually converted a lot of our resin transfer molded parts to a DCP reaction injection molding process. This is an example of a tank. It's molded in 2 halves and then bonded together. This is one of our high volume wastewater pumping systems for collection systems. We do both collection and treatment. We've just been talking about treatment vessels, but we do a lot for pressure sewer pumping systems. Here's an example of one of our aluminum molds in a horizontal press. This particular part is a 185-pound part. It's injected in about 50 seconds and about a 10-minute button cycle time. And my last slide here, just for fun, a number of years ago, we developed a way to infuse using a clear resin digital images in the top of a ping pong table. These are 100% composite. There's no metal. It's 100% glass fiber, foam core, and resin. And that's it for my presentation. Like Dale said, I'd be happy to take any questions.
Thanks, Eric. None, we'll see if one comes up during our little Q&A here that you and I'll have. What kind of resin system? I know the DCPD I know is an unreinforced system, but the fiberglass reinforced systems, is that mostly vinyl ester for corrosion resistant purposes, or are there other resin systems that you're using?
So we use isophthalic resin primarily for most of the water and wastewater. We've done a lot of C581 testing to show that it's more than adequate for most municipal wastewater. However, a lot of the systems we do, like the selenium treatment tanks you saw, those are all vinyl ester. So we do use vinyl ester for a lot of applications, industrial applications.
Okay. What's the highest temperature any of these see?
So some of the vinyl ester tanks may get up to 200 degrees Fahrenheit, usually not on a continual basis, though. Most of the municipal wastewater systems, they're not going to see over 100 degrees Fahrenheit. I mean, the bugs, the treatment system is going to fail miserably if it gets too hot.
Yeah, certainly you've got the one that can get pretty cold if it's in Alaska.
Oh yeah,
the mountains of British Columbia.
In Alaska, the engineers on that treatment system asked us if their power went out, how long before that tank of water would turn into a block of ice. I just told them, you guys are the cold weather expert engineers. You guys need to figure that out.
Yeah, well, I mean, if there's foam core involved, it'll take a while anyway.
So they did do that analysis, and they said it would take about 2 weeks.
Yeah. Okay. Even at those temperatures.
Yeah.
Okay. Well, we've got somebody who's on as a graduate student asking if there are internship opportunities for graduate students at Orenco.
Yeah, we have interns every year, multiple engineering disciplines.
Okay. All right. So we don't have any more questions at the moment. Thank you. Thanks a lot. That's amazing. How you go from, just figuring out a different way to make your tank to transform it into all kinds of building systems and other structures as well. So, and then obviously the bridge structures are pretty exciting as well. As you know, we have a big infrastructure problem here in the United States, and
yes, we do.
Look forward to working with you on solving some of those. Okay. All right. Thanks, Eric. All right. So we're coming to our third presenter of the day. It's Professor Uday Vaidya. Uday, you want to fire up your screen share? We're seeing this. There you go. It's all yours.
Okay.
You may be muted.
Hey, thank you, Dale. Yeah, thank you all, Scott, Eric. That was awesome, excellent. So I'll just switch some gear here, and so this briefing is really tied to workforce development. As you know, there's a lot of need and expressed interest from a lot of community and employers about workforce development in composites, which is a national and international need. So ACE is America's Cutting Edge. It's a program that is funded through the Department of Defense under the IBAS office, which is Industrial Base Analysis and Sustainment Program, a segment of DoD. So as you probably know, IACMI was primarily a DOE institute, but through this program, after the year 5, IACMI branched into also serving some of the DoD projects. So this project is funded by DoD, and at the same time, there's a lot of collaboration, of course, between Oak Ridge National Lab, University of Tennessee, and IACMI. Joni is the workforce director for IACMI. Tyler works closely with her as a workforce staff member. And this program has two facets to it. Metals, which is a significantly large component of ACE, is metal machining, serving the America's machine tool industry, and composite. So today I'm just going to brief you in the short time I have about the composites activities we have been doing. So essentially, you all are familiar with the ecosystem in East Tennessee. There is the IACMI right here, Oak Ridge National Lab, University of Tennessee. A lot of the Oak Ridge units, such as the manufacturing demonstration facility, the carbon fiber technology facility, and many units at University of Tennessee around composites, manufacturing, characterization, biomaterials, and so on. So essentially, that's the makeup of participants when they come to these activities. They get exposure and viewpoint from this entire ecosystem. We also go over the IACMI as an institute with the participants and generally get them oriented about what to expect. The workshops that we run typically service anywhere from 25 to 40 participants. These are students from community colleges, even high schools, as well as college students, and teachers, some of the teachers who take back the information back to their schools and then essentially implement it there in their classrooms to their personalized settings. So that's really the background of ACE, and I will go straight to the information that we had provided this coming July. But all these are examples of the type of information we give them about introduction to composites, applications of composites, and so on. So coming to this slide right here, I will just mention that we have developed a whole range of projects, activities for experiential learning for composites. And these include everything from skateboards, rockets, ballistic panels. Each of them is a structured activity which could be tailored for 1 day, 2 day, a full week, based on the availability of the participants and what they're planning or hoping to get out of it. So this mission also has been spread across the country. We are working closely with the New York, Long Island facility with Phil Rugail and his group, a lot of schools in the between Florida, Minnesota, as well as throughout the country, as well as doing workshops in-house at the University of Tennessee. So we ran this recent workshop in July of this coming year, just a month or two ago. And let me first go to this mention, the activity was tied to building a composite drone. So you probably know there's a whole variety of drones, from all the way from small do-it-yourself kits all the way to large ones. We want to do something manageable for the students. So we had started with a basic idea with a quadcopter, which would require them to design the entire base structure completely personalized to their imagination, as well as go with different ways of building the cover, as well as the unit that carries the camera. Everybody had standard blades that they used, but the rest of the structure was fully customized, and the electronics was common across the group. So this was a 5-day activity. I will be happy to share these slides, but the way we structured the 5 days was in the morning of the first day, we introduced the participants to the program, introduced them to what are composites, because some of them came very fresh to the workshop with no knowledge of composites, and then essentially set the stage for them to understand what to expect. And that morning as well, the CAD information was provided to them, or training using Fusion 360. So somebody with no CAD experience was able to actually build their design, conceptual design, by the first afternoon. So in 1 day, we were able to get them up to speed on the CAD activities. On the second morning, we introduced them to the composites machining, cam paths, and these basic ideas of how do you take what you make and then actually go ahead and see how you would machine it. Then we went into material selection and manufacturing methods. We basically demoed them vacuum infusion, compression molding, extrusion compression molding, and additive manufacturing. So these were the 4 processes which they were exposed to, and they had to decide which one they'd use for their particular design and be able to implement that in days 3 and 4 to get all the parts required for their kit ready by the afternoon of the day 4, ready for assembly. And it was amazing how well the participants did. We had 38 participants in this round, and that also included teachers who provided their inputs along the way. So that's the agenda. It's very short, small letters, I understand, but just to give you an idea of how that was done. Also, the mentors for this were graduate students. So it was literally train the trainers, meaning graduate students were actually serving as mentors for the participants. So it was very hands-on and interactive in nature. So these are some examples of to give you an idea how it went. So this is the session where the grad student is Kaustubh is going over Fusion 360 and the philosophy, how to design. And the participants actually had their own computers, which they were able to quickly practice and then come up with their own designs. All this was on day 1. On day 2, they sat as a group and collectively evaluated each other's design of the base. And each group had very different ideas about how their base would be. And this is kind of their interactive network of exchanging ideas and thoughts about how it would work or may have some challenges and so on. So interactive input of design is a key point in any engineering application. Then after this is examples of parts they made. They actually produced plates like these. This is a compression molded plate. This is an extrusion compression molded plate. This is a vacuum infused plate. And they took it through the machining operations. And you can see that each of this is a different design from each team. And many of them had weight savings through slots and holes and other things. So very creative designs. And the caps that they made. So the caps itself were produced by additive manufacturing. This is where they got exposure to creating CAD files and then printing with either ABS or nylon. But these each group made their own caps this way. And then machining itself, we have a Haas VM3 as part of the ACE program. So this is John and Will, who are actually, again, senior undergrads who mentored the participants on machining each of their plates into the designs that I just showed you. All this was achieved on days 3 and 4. And then this is Sam working through showing the teams how to assemble their drones. And this is Tyler actually going through his analysis of each of their designs. And they're all aerospace majors, which is really fantastic how they interacted with the team. And these are teachers as well as Kansas City plant employees who actually attended in the capacity of teachers because they are training their own communities on composites. So this is why they were so engaged in it. This is Marco from University of Puerto Rico, visiting faculty. So the group makeup was very diverse and very engaging. Also, we invited the teachers to serve on a panel where each of them are high school teachers or employees of industry or their own companies. And each of them provided perspective to the students, participants on career goals, what worked for them in their career, what was their career path, and kind of do's and don'ts. Again, a very useful exercise for the young minds to get an experience of what to expect in their own future. Here's Alex showing off his design. At the end, each of these folks build their own individualized drones, if you will. And these are examples of the kits that got assembled at the end with the caps, printed caps, whatever method they used to reuse the base, assembled. So every single one actually flew. And there was a competition. I think Mark has a LinkedIn post with the video here. I'm sorry, I didn't catch the video this morning. But very interesting, we had this as the torture path for them to cross. So they had to go round and round this like 10 times to show that their design was robust and actually functional and followed the intended path. So this was a competition mode, like a college basketball shootout, if you will. And I would say they did fantastic. So these are just examples of that. This is a whole team for this workshop. And I'm giving you one example of many such activities that our team has conducted. And I go back to this slide to mention that we have about 14 AR, VR modules now, which can be taken to sites. Any participants can wear them and get a virtual reality experience of the wind manufactured in Colorado under Derrick Berry, or the manufacturing at the carbon fiber plant at Oak Ridge, and so on. And every single one of these is a fully fledged out activity. And Dale, I'll stop there. If people have questions, I have like 1 million slides, but I'll probably be best to stop here. So.
Thanks, Uday. Yeah, there's, I don't see any questions in the chat. So if you've got anything, we have a couple of minutes if somebody wants to ask a question. But where do you go from here? What would be the next fun thing to do?
Sure. So this activity was a 5-day activity. Obviously, in a given semester, 5 days is too long. So we're obviously looking at making a 2-day, like a weekend activity of this, where everything which did here could be easily accomplished, like a Friday, Saturday, or a Saturday, Sunday. And therefore, the dissemination could be very widespread across high schools and community colleges. That's one of the things. All these activities have been compiled into a book as well, so people can take advantage of that and get information from there. But we just have to grow the knowledge base and get people excited about composites, right? I mean, there's not a standard curriculum which goes into everything I've said here. But in this way, you learned about materials, machining, manufacturing, product design, assembly, electronics, the whole thing, right? But I mean, it looks like it's a small part, but all these fields came together for their, I guess, assembly and integration. So,
yeah, I know Mark Morrison is on. I don't know if he could pop in. So, yeah, I don't know if that video is available on our website or on a LinkedIn site or on the.
it is on LinkedIn. I can pull it up and send it to you to share with the team.
Okay, we're running kind of out of time now, but yeah, so the video, yeah, I've seen the video. It's pretty cool watching all those drones race. So it isn't just a matter of building them. It's, you know, they actually fly them, and it's pretty significant. It's very impressive. Okay, well, we are near the end of our hour. We're going to give everybody a minute or two back, and I want to thank everyone for attending today's Innovation Insights episode, and be sure to join us next month on October 24th for the next edition. So thank you very much, and we will end our program for today.
Thank you, Dale. That's the video, I think.
It's on YouTube. Yeah.